So it's my great pleasure to host Iryna Gurevych. He was my professor at UKP Darmstadt for a long time. So she's a professor of computer science and director of UKP Lab at the Technical University of Darmstadt, Germany. Her main research interests are in machine learning for large-scale language understanding and text semantics. She has received many awards, which I cannot list here. There are just too many. But some examples are some ACL Fellow Awards in 2020, the recent ones, and the first ever Hessian Loewe Distinguished Chair Award, around 2.5 million euros, 2021. And she's also a co-director of the NLP program within ELIS, which is a network of excellence in machine learning. She's also the current president of ACL, which is the most important association for NLP. And she recently received an ERC Advanced Grant, and I guess she will be talking about it today. Yeah, the stage is yours, Iryna. Thanks a lot for joining today.
Thank you so much, Gusta. I'm delighted to be here. So welcome to my talk. My name is Iryna Gurevych, and I'm going to talk about modeling text as a living object in context. This is joint work with many people, but before all, I would like to point out my collaborator, Ilya Kuznetsov, who is a project co-leader at the UKP Lab, and he's also present here in the talk and may join the discussion. A lot of text, a lot of work nowadays is text work. I mean, given ChatGPT and all the attention that it has right now, I don't think to elaborate on this a lot in this audience. In business, education, and research, we spend most of our time actually working with text. And what humans are very good at is to handle small amounts of text. We make the most out of our background knowledge, context, and common sense. But we are not a good model at all to handle large amounts of text, because our memory and attention are very limited, and reading a long document is very hard, takes a lot of effort. So also navigating a large collection of texts is a very hard task for a human. In the past decades, some things got much easier thanks to a great advance in artificial intelligence and NLP technologies. We have good search, we have good recommenders and information extractors. Machine translation works really well in everyday life. And recently we got new human-like chat interfaces like ChatGPT. And most of these applications are powered by transformers, as we of course know. But some things still remain very hard in today's NLP. AI does not help us appropriately to find where the information comes from. And we still have very little tools to judge the information quality that we consume. And also AI for reading assistance, especially non-document scenarios, is very limited, and there is not much AI assistance for collaborative writing. Even though nowadays we have convenient tools like Google Docs and Overly, those tools are to some extent still at the level of paper and pencil comments and don't include any advanced AI capabilities. Why is that? When you think about a lot of text, you probably think about a long book or a pile of documents. This is static text. But a regional history of a single document or a chain of related documents and references are also a lot of text. And humans are equally bad to handle this. Treating text as a static object is a well-known tradition in NLP, and most successful applications of AI that we...
Yeah, sorry to interrupt. There is some echo. Would it be possible to use some...
Yes, maybe? Just a second, I need to connect my mic.
let's use this. Okay, so treating text as a static object is a very long tradition in NLP, and most successful applications of NLP that I talked about before treat text as a static document. We have pretty mature technology for that, and many great applications, which I already mentioned, like search, information extraction, or translation. But we lack mature technology to analyze texts in context that evolve over time. And this makes it very hard to develop approaches that could analyze fine-grained cross-document relations. Yet we need such approaches in order to develop new applications of NLP for example, for information provenance or for reading and writing assistance in order to handle long documents and large collections of documents. And while there exists some work in limited domains like Wikipedia or citation analysis, a general methodology, tasks, and data to study text as a living object in context are still missing in NLP. To close this gap, our lab has started this InterText initiative, building upon the intertextuality theories from literary studies. We look at text as a living object in context. We propose to see each text along two axes, time and context. And when a text is updated, it moves through time. When another text talks about the text, it moves through context by reference between the two texts. In InterText, we develop new conceptual models, design tasks, and create methods and data sets to analyze fine-grained relations between texts in time and in context. This is our research team funded by several coordinated research projects, including a new 5-year ERC Advanced Grant that KUIS has mentioned that will start on the 1st of April this year. And we have a website where we will continuously report our progress about this initiative. So in the talk today, I'm going to give you the basics, since this is a very new project, and also more results will hopefully follow in the next years. By the end of this talk, you will think about texts ideally in a new way. You will get a glimpse into how we model text as a living object in context. And hopefully you can discover some useful corpora or tools that you can use in your own work. We will talk about the foundations of intertextual modeling. We will introduce 3 new tasks, linking, versioning, and inline commentary, and a whole range of resources and tools that we developed to get intertextual NLP started. In the end, I'm going to answer the questions, and please note the slide numbers so we can go back to the slides you're interested in, and you do not need to worry about copying the links because KUIS has already circulated a small document where we collect all important links with the background information for my talk. The talk today is also centered around a particular use case that we consider, specifically academic peer review. Scientific documents are a great research target because you have long documents connected by citations, often in multiple versions. However, published documents are just the tip of the iceberg. Most scientific publications go through peer review, and many of you, of course, have experienced this. You submit a paper, a reviewer gives you feedback, and you resubmit it until it's good to go. So there is a lot of very interesting data that has hardly been studied so far. So this data is great for intertextual analysis because it has texts in context that evolve over time. And all of this usually happens within a reviewing platform, so the data is comparatively easy to collect. And peer review, of course, as we all know, has many issues. Because of this, NLP for peer review is a rapidly growing area right now to which we want to contribute new tasks, methods, and data sets. With that, we move on to the foundations of intertextual modeling. Treating text as a living object in context means putting it on two axes, as I have already explained, time and context. A document changes over time and is discussed by other documents. In our project, we make a simplifying assumption and focus on two documents at a time, and they don't need to be consecutive documents. Given those two documents, we want to find fine-grained relations between them, and this is quite similar to traditional relation extraction in NLP. Like in an example to the right, we find a span Barack Obama connected to another span politician and label the relation between them. However, there's the question, what should our relations cross-document be? From the theoretical work on intertextuality, we know that cross-document relations can differ by type. For example, metatextuality is defined as text about text. They can differ by explicitness. Some relations are clearly marked, like quotations or citations, and others are implicit, for example, allusions and plagiarism. And finally, relations differ by granularity. For example, a citation might point to a whole document, a page, a section, or even a line in the text. And here we run into the first challenge. Current NLP treats text as a flat sequence of characters, subwords, or words, like in the example on the slide. It is a long tradition, and we see document as a wall of text, so which works well for many applications. However, if we want to draw intertextual relations between texts, this view is not very convenient. Humans use document structure when they work with long texts. So for example, if we read a scientific paper, we can see there's an abstract, there's a conclusion, the methods section, and so on. So if we see the text as a sequence of characters, it means that we lose all of those document structure. That is very important. And a transformer does not know what a section or a page is, and so we cannot draw a relation to a section or a page. Besides, we also lose multimodal elements like tables and figures. A solution to this is to see text as a graph. You can think about syntactic trees that split a sentence into coherent groups, like a noun phrase, a verb phrase, and so on. And in a similar way, any document has logical structure like paragraphs, subsections, sections. And if we represent a document as a graph, many things can become much easier. We can draw relations between text units of different granularity, for example, from a sentence to a chapter. We can preserve multimodal information like figures and draw relations to them. We can get additional structural signal for free, and we can easily represent multiple documents within the same graph. To formalize this idea, we have developed the so-called intertextual graph. It's a specification that outlines the core relation types. They are parent, next, and link, coupled with a Python library that converts texts from different formats into a unified graph representation. So you can take a Wikipedia article and a research paper, convert them into graphs, and start drawing links between them. We have used this library in several studies, and we are constantly extending the library. And as you can see, real graphs are more complex than our example from before. But the core idea is very simple. We use document structure as a skeleton for intertextual analysis. Now, switching from sequence to graph raises another question. Because transformers see text as a sequence, so we have this limited view. And even if we would give a transformer a structured document, it would not know what to do with it. This is not a fundamental limitation of transformers, though. So we want to study in this project, how can we communicate this new information to the transformer? So how can we infuse this information? This is an open research problem. A transformer works by encoding the input sequence with a mixture of token and position embeddings. And this information is passed through a number of blocks that update vector representations for each word based on other words using self-attention. And then the output can be used for decoding or to directly make predictions for a target task. There are many different aspects of text structure that can be infused. For example, distance in the tree or a node type, like title or section. And besides, there are many places where this information can be added to a pre-trained transformer model. We can create new special tokens, we can tweak the position embeddings, we can play with attention. Structure can be added at lower or higher levels during pre-training or during inference. Finally, how do we know that it worked? We need to find tasks where structure infusion would be beneficial. And this is our work in progress currently, and more insights on that are going to be available in the next months. As a quick glimpse into the current results, here is how structure infusion affects the answer generation and evidence selection on Casper, a question answering dataset on scientific papers. As horizontal bars, here we have a long document LED transformer. So this is our baseline. We compare these baselines to the blue bars, which are LED pre-trained via T5 style masked language modeling objective, enhanced with different kinds of structural information. So these different kinds of structural information are separate bars. And the main conclusion that we can take away from this analysis is that the strongest improvements are from combining positional embeddings and input sequence modifications. So these are the bars on the very right. However, as I pointed out, these results are very preliminary. So this is just a single data set, and we will have more results in the near future. For now, I'd like to proceed to the next chapter about the tasks that we consider. So far, we established that one can treat text as a two-dimensional object in time and in context, and we focus on document pairs and treat each text as a graph which preserves document structure and takes care of relation granularity, format differences, and other technical details. And now we move on to the relations, their types and variations. We have identified three core relation types that can exist between two documents. The first one is linking, a text talking about another text. The second one is versioning, a text being a revision of a previous text. And the third one is inline commentary, a special type of linking that occurs when you make a highlight or annotation on a text. We will get to that in a few minutes. Each relation can be explicit or implicit. And to recap, explicit relations are clearly signaled in text. For example, page 5, line 12, or a citation, while implicit relations are not marked, like plagiarism or general reference without a citation, like in our example on the bottom. The idea to use SVM here is not new. We define linking as a two-step task. Given a document A that talks about document B, we want to find anchors in document A and link them to targets in document B. And there are two kinds of linking, explicit and implicit. First paragraph of section 3 is an explicit link, and the use of mosquito traps is an implicit link. This task might in general sound familiar to you from other related tasks like citation span detection, plagiarism detection, and evidence detection in fact checking, which are well established. And linking is basically a generalization of these different tasks. So with this task definition, we ran a corpus study in peer review to learn more about the task. We collected a large corpus of papers and reviews and annotated them with explicit and implicit links. And we found that explicit links are pretty easy to work with, which is not surprising. We can easily find link anchors, and usually they point at precise locations in the paper, which are very easy to pinpoint if a text is represented as a graph. There are different kinds of explicit links, and we have built a simple rule-based system to draw explicit links between documents, which worked reasonably well, and the errors were easy to fix. And with that, we could study how people use explicit links in peer review. For example, we found that people mostly use quotes and section pointers, and very rarely reference on a paragraph level, for example. Then we move on to implicit linking. Now our anchors are vague and implicit, and our targets are unclear, like in the example to the right. This makes the task very challenging, and we ran a human annotation study to learn more about the task. Imagine for a second how hard it is. You are given a 10-page paper and a 3-page review, both of which you have never seen, and you need to go through the review sentence by sentence and figure out which parts of the paper talk about the use of mosquito traps. This is a very hard task, and to make the study feasible, we implement an annotation assistance approach, which suggests top 5 similar sentences from the paper to a given sentence. And this way, we annotated 21,000 sentence pairs with labels, link or no link. We reached moderate agreement of 0.54 in kappa, and we wanted to learn more about the task. Maybe our annotators did not know the topics well enough, since we deal with scientific context. So we hired 2 expert annotators in the domain of the papers, and we found that, in fact, the task-specific training matters more than domain expertise, because the agreement among domain experts was even lower. Maybe our task is subjective. To study this, we asked our annotators to relabel some items after several months. And yet we found that the self-agreement is not much better than the original agreement, so roughly the same level. So the task is not really subjective, it's just a very hard task. So future work will need to investigate how to make linking easier to annotate. We now move to the second task, versioning. In versioning, we are given 2 revisions, A1 and A2, and we want to find edits and label them. This might sound familiar from related work in Wikipedia edit analysis and student essay revisions. So in our definition, versioning is a general form of such different tasks. We distinguish between 2 kinds of revisions. Short scope revisions are minor edits, usually with one intention, like a paraphrase. And long scope revisions are major edits that might encompass many complex intentions up to a complete document rewrite. In many real-world scenarios, we deal with long scope revisions, which are considerably more hard than the short scope revisions. To study versioning in the wild, we again conducted a corpus study in peer review. We developed an automatic graph aligner based on integer linear programming and paragraph similarity that would help us match paragraphs from the first and the second version of a paper with additional constraints, like only matching nodes of the same type. All the non-matching paragraphs from the first version are considered deleted and from the second version added. We got good alignment performance out of the box. So at least on the paragraph level, our approach works well. And we note that on a sentence and sub-sentence level, the situation is different, and we did not do any labeling yet on those levels. So the task is far from being solved now. Yet, even with this simple approach combined with linking, we can study fine-grained cross-document relations between papers, reviews, and revisions. We can answer questions like, what is the intention of this sentence? What is it about? What change does it cause? What parts of papers receive most criticism? Which comments trigger most change? And more details can be found in our article. For example, the plot to the right shows that the parts of the paper discussed by a peer review are almost twice as likely to be changed in a revision. This is very powerful analysis, which can help authors, area chairs, and reviewers navigate texts better. We note that this kind of joint analysis is made possible by the intertextual graph, which allows us to switch between granularities and quickly aggregate linking and versioning information from several documents. But we just scratched the surface with versioning. There is a lot more to be done to enable versioning on sentence and sub-sentence level and to interpret the edits. This is very relevant related work to Wikipedia edit studies, student essays, and use. And we would like to integrate these different types of corpora in our benchmark in the future. There are many open questions to resolve. For example, what is a good unit of change? Is it sentence, word, or character? How to interpret, edit intentions? Which inventory is good for that? How to annotate large document revisions? And I hope there will be more news on this topic in the next months and years. Finally, we move on to the third relationship type, inline commentary. Leaving annotations on text is a very natural behavior of humans, and humans have been doing this since the invention of writing, basically. Highlights and comments are a key part of text work, from printouts to PDF readers to writing platforms like Google Docs and Overleaf. We believe that AI for inline commentary has great potential to change the way how we interact with text. However, this text type so far is being overlooked by NLP. There is virtually no data, no tasks or methods for it. And inline commentaries are very different from traditional NLP annotations. We notice that inline commentary is structurally similar to linking. An inline commentary has a highlight in the main text and a body, like in our example above. Now we see that now if we see text as a graph, then inline commentaries can be simply attached as new graph nodes linked to the targets, and we can even model discussion threads. This kind of data has great potential for the study of cross-document relations, both in context and in time. Yeah, we need to overcome the lack of data. So convenient data collection tools for inline commentary become a crucial point. To close this gap, our lab has developed CARE. CARE is a collaborative assisted reading environment, which is very similar to a PDF reader, but with collaborative commenting, like in Google Docs, data expert, like in Label Studio or Inception, and with onboard Transformers integration. It's a very interesting tool because it allows you to collect naturally occurring annotations, but also it collects some behavioral data like clicks and page scrolling, and allows you to incorporate an AI assistance model, which will just act as another, so to speak, reader of your document along with the humans. For example, an AI assistant would suggest some related works based on the user's comment or quickly tag the comment with sentiment. The whole system is implemented from scratch and is quite compact, so it's very easy to extend and modify it. You can use it to collect inline commentary and behavioral data from PDF documents, or you can make some lightweight NLP model automatically label comments in real time and run, for example, user studies. We just released this tool a few days ago, and are very curious what the community will do with it. So now, finally, I would like to speak a bit about the data sets. A data set that doesn't have a license and leaks personal information is hard to use and to build upon, and prohibitive in as a current time where ethics and legal issues become crucial. Earlier, NLP dealt with static documents, and it is already challenging to collect such clean data sets. However, static texts often come from one source and one group of authors, and we have some licensing standards and reasonable defaults. Now, if we move to study living text in context, we are exposed to new document types that historically have been a gray zone. What is, for example, the license of a paper draft? How to attribute the author of a blind peer review? How to prevent information to leak through context? And there are many important questions that determine if the data can be used for research and openly distributed. So the data set collection becomes a lot more challenging. Peer review is a good example of a complex data situation. There are three ways people in NLP have solved it so far. First, corpora of peer reviews were just scrolled from Open Review and Europe's. So this started the research direction, but it's problematic in all other ways. Peer review puts no license on peer reviews, and neither reviewers nor authors gave consent to their data being used for AI assistance. The second way is to look for open sources. Indeed, there are some fully open reviewing platforms that publish papers, reviews, and revisions, and even reviewer names. However, most research communities do not do that. And the third hard way is to set up a data donation workflow. One can go to any conference and ask them to implement a workflow where reviewers and authors give consent and transfer license for their data. And later one can collect and publish this data. And this is the most flexible way, but of course it is associated with the most effort. To make it easier, we have developed a general purpose data collection workflow for peer reviews according to this third paradigm of data donation. We first ask the reviewers if they want to donate their data. If not, we stop the process. Then we ask the authors and wait for the paper to be accepted. And only if all three conditions are met, we collect the data point. This is a carefully designed workflow with consent forms, license templates, and open source implementation. And we published a paper about it where we studied how donation-based data collection affects the data. And there are, of course, various kinds of biases, for example, towards acceptance of the paper. So currently, we run this data collection at ACL rolling review infrastructure. So if you stumble upon a data donation request, we would be very happy if you consider contributing your data. To this point, we have collected two major corpora of papers, peer reviews and revisions, to help study cross-document relations in peer review. The first corpus is F1000 RD. It is a collection of papers, revisions, and reviews from the F1000 research platform. It is a fairly large corpus that has more than 170 papers and more than 220 reviews, about 500,000 words in total. All documents are annotated with linking, versioning, and discourse tags, and we have published this corpus along with our explicit linker and version aligner and the first version of the Intertextual Graph library. It's a first-of-a-kind resource to study text as a living object. The second corpus is our new work, NLPeer, where we have a preprint already available. We have combined openly available and donation-based reviewing data to create a one-stop shop for the computational study of peer review. It's a massive resource that covers over 5,000 papers and 11,000 peer reviews, more than 4 million words in reviews alone. And it combines ethically sourced data from different research communities and reviewing systems in a unified format, and is coupled with several practical reviewing assistance tasks, some of which make use of cross-document relations and others are more applied, like score prediction or pragmatic tagging. It's a foundational resource for both intertextual NLP and NLP for peer review analysis, and both preprint and data have become recently publicly available. So this brings me to the conclusion. In this talk, we discussed a new approach to text as a living object in context. We talked about seeing text as a graph and the benefits and challenges of this approach. We introduced three new tasks, linking, versioning, and inline commentary, and we shared our first experience in making these tasks operational. Finally, we talked about collecting data for intertextual analysis and presented several resources that can serve as a great starting point to study cross-document relations. If you wanted to do so, those data sets have become already available for you. If there are only three things to take away from my talk, I think they are as follows. First, any text is written and read in the context of other texts over time, be it a tweet or a research article. Second, studying the relations that occur between these texts would enable a new generation of AI tools to help text work, but conceptual models, tasks, and data sets are still crucially missing. And we propose to focus on three main phenomena in cross-document analysis: linking, versioning, and inline commentary. And finally, we think that peer review is a great application domain for the study of text as a living object in context and beyond. And there are tools and resources available to get started already. Some of the work we talked about is work in progress, and we hope to have more updates soon. So I'm looking forward also to your comments and feedback. I'd like to emphasize that though I presented peer review as the main application domain of cross-document analysis, it's just our first use case. So there are many more very challenging use cases, for example, in the domain of software engineering, where you have software code, comments, and social media data, or the analysis of religious text with different commentaries. So Wikipedia, of course, news and blogs. So there are many, many applications of cross-document relations, and we want to develop the general technology that can be then explored in different application domains. And also I've presented the intertextual graph library and our tool KUIS to collect inline commentary annotations. Finally, we are looking into other applications of NLP to peer review, and there will be some shared tasks, and also there will be a Darkstuhl seminar 2024 on this topic. So we invite you to explore our work, and if you would like to stay up to date, feel free to add yourself to our informal newsletter. And the links have been already distributed to you, or just reach out to us. Yeah, thanks a lot for your attention. I'm looking forward to your questions.
Thanks a lot, Iryna. All right, so let's get to questions. Does anyone have any questions?
Yes, Hojam. Can I start?
Yeah, please do.
Okay. First of all, thank you very much for this wonderful talk. I really enjoyed it. I have 2 questions, please. The first one is, I'm wondering if this work can be extended to dialogues. You know, dialogues can have various number of terms, and they will define the structure. Also, dialogues meet the 2-axis structure you proposed, which is context and time. And then the second question, for the intertext graph representation, do you think it can help in multimodal documents? If so, do we need new relation types for that? Or maybe linking it by itself should be enough and sufficient? Thank you.
Well, thanks a lot for your questions. Great questions. So for the first question, the answer is definitely yes. We actually got exactly this comment from one of the reviewers of the ERC proposal, or not a comment, but a suggestion to consider graphs, dialogues, because they have a lot of structural information, and we are planning to do so. So there was one student in my lab that will be looking into this. So regarding the multimodality, so we think that the intertextual library is very generic right now, so we can include multimodal elements, but we currently plan no work on kind of analyzing multimodal information. So this is just out of scope of our current activities in the project. So we put multimodal elements as nodes in the intertextual graph and connect with parent and next relations plus links. So we keep source code not to lose the data, but I think to explore this more and how to make use of it, that would be a separate research project that can build on top of our work. Maybe Ilya has another comment on this. If you have a comment, Ilya, please feel free to jump in.
No, I think it's it sums it up.
All right, any other questions?
So, Iryna, can you hear me?
Yes, I can hear you.
So I have a question. This is more like an open question about using transformers, transformer architecture to model this type of intertextual relationships. You mentioned that one can introduce a special token just for these specific connections. My question is, so we have this tokenization step. You mentioned text as living objects, but indeed, tokens are also living objects, right? Like about 10 years ago, we don't have the term transformer, meaning this neural network architecture. So it seems to me that the models should have some capability on the fly in an online fashion to somehow decide to use a new token at a certain instant. Would that make sense? I know that this is a complex issue, but did you just think about this?
Well, I have to admit that, well, this sounds like an engaging idea, but we have not thought about this, you know. So, but that sounds kind of interesting. So how can we update the transformer model with some new tokens that emerge from the analysis? So I think it would be definitely very interesting to explore. Ilya?
Yeah, so just to rephrase, to make sure I understand correctly. So what you're asking is that, for example, if we have a text and we have some token in this text, in real, like for us humans, it's very easy to switch us to interpret the text, a token in a new way, right? So for example, if you have a text and you have some term and you define it, you say, in this work, we treat this as this, and then this word is used in the sense throughout the text. However, the transformer represents generalist knowledge, right? So it would be hard to, so one would need to come up with a way to update the representation of this token. Is this correct?
Mm-hmm. Yes, and also I'm just imagining that, for example, you may use an external knowledge base. Like, for example, in the example, we have this Barack Obama. So those type of like specific tokens may arise. For example, in the example you showed us today is peer review. There may be some new terms that arise at a specific time. So then, again, I'm not so sure, but it seems to me that this tokenization should be also like a dynamic process, creating and adding new type of special tokens on the fly.
Yeah, so yeah, it's a very interesting point, and I think it is not necessarily in the scope of what we do, but basically, there is a bit of research on time sensitivity of large language models, right? Because we have texts that evolve in time and in context, but we also have large language models which have been pre-trained on some corpus, right? And then since then, the world has evolved, more texts have appeared, and maybe some things have changed. And yeah, so these, of course, go hand in hand. The question is whether the meaning of words changes. So the question is, what is the optimal time scale for this? Because in InterText, we are interested in relatively short-term changes, right? So like, for example, you and me are writing a paper together, right? And we update it, and we want to connect revisions of this paper. And most changes in the meaning of words and so on, they just take much longer time. So it could be that some methodology that we have is relevant for this, but it might also be that on the scale of intertextual modeling, we might not necessarily feel this general semantic shift of words over time. However, for the situational context where, for example, like you just redefine a term and go with it, of course, it would be very interesting to look into this methodologically.
Okay, thank you so much.
Regarding that, I have just one comment. So the problem you have mentioned is kind of studied in the domain adaptation works. For instance, you have a pre-trained language model and you want to shift the domain to medical. text where you have a lot of new words. So basically, you use some kind of adapters or some dynamic training to include those words into the known tokens. And there are also some ongoing work in lower source, but I'm not an expert on this. I just scroll through a few words. And yeah, I'm curious about how you model time, Ilya. So we represent text as graphs, and then we also talk about versioning and linking. So wouldn't it be easier if we just put the timestamp on the document? Or do we have this time information, and how do you treat it?
So of course, the documents are timestamped. So this is an assumption that we have. But for versioning, we are interested in finding the semantics of the difference between the two versions. So for example, I have two documents, one from today morning, one from the evening, and then I want to find what changed and why did it change, right? So we are interested in the meaning change between these two timestamps. So I hope that answers it, if I understood your question correctly.
Well, I think that the timestamp is sometimes available and easy to get, like in the scientific domain, for example, but in other domains, it can be very difficult to get. So basically, the time needs to be read not literally, but more like we know, for example, one version of the text is the earlier version, so relatively earlier than the other one. And how explicit we have the information about time depends on the domain of application.
Yeah, so maybe I was curious if you have like a spatial link between new documents and old documents, like parent-child kind of relation, or it's not relevant.
This is a very interesting question. Actually, we did have a bit of an experience with this, because at some point we wanted to extract peer reviewing information, like from OpenReview, which became the NLPeer resource. And we wanted to extract papers, reviews, revisions, author responses, and like all this dialogue stuff. And it turned out that it's very hard because basically OpenReview stores the time of last update and not the time of like when the thing is first published. So you get this like very complex network. So someone published the paper, the thread started, someone updated the paper, someone updates their response. Then the thing in the middle doesn't make any sense anymore, and so on and so on. So it gets very tricky. And because of that, it might actually make sense to keep explicit connections and keep track of these connections between parent, like source, say version 1 and version 2 documents, independent of the timestamp, because timestamps might be not always reliable. So that's a very interesting point. Yeah.
Yeah, I have one more question. So modeling long context is a known problem, and I've seen you are using transformers that can handle longer context. But will it be a focus of this research? Are you going to focus on coming up with new architectures, or when you represent text as graph, this problem is kind of solved? What do you think? So I guess representing text as a graph kind of makes your context smaller, right? So you have links and you have smaller context, and it's easier to model. That's my first impression, but just wanted to ask.
So we are not planning to come up with new architectures for long document processing, but rather build on top of existing architectures. The research questions in the project are mainly concerned with domain adaptation. So we want to use adapters and combine more than 2 adapters, and also scale adapters to long document contexts. But the long document transformer architectures we leave to other people.
Okay.
Ilya?
Yeah, Ilyas.
Yeah, I might add a bit to this. So basically, it would be wonderful if we could train a long document transformer that is structure aware out of the box, so that has only seen structured documents and is fine with them and then can utilize the structure efficiently. However, the problem there is that we do not have a unified format for structured documents. So almost any document in the web you can find has some kind of structure, and we have methods to clean it up, which means convert it into plain text. And that's why we have long document transformers, because we can collect enough data to train a good transformer. But for the structured documents, we would need a unified representation that the transformer would understand. So maybe one day when intertextual graph is really mature, we can run a lot of text through it and actually build a full pre-trained model. But first we need to, there is a lot of technical work involved as well. So we focus on other things first and use someone else's long document transformers as a base.
A good approach. I think Gürkan has a question. Gürkan, can you unmute and ask the question?
I wrote the question.
Okay.
So we can read the question in the chat. I would like to ask about the complexity issue. So in a limited scope, such as peer reviewing, it is not much of an issue. However, how can we extend or upgrade the model to, let's say, consume lot more data as in other large language models? So it's indeed a very interesting question. So in our project, we focus on 2 documents at a time because we first need basic technology and basic understanding of cross-document relations and so on. And I think later one could scale to larger graphs, and it would be great to have one huge intertextual graph with many documents all connected to each other. But this is, again, also kind of beyond the current scope of what we do. So we hope we can kind of interact with other people interested in that question. Because obviously what we propose here is like a new paradigm of studying interconnected documents, and there are all sorts of issues that could be studied, but of course we cannot cover for all of them in the scope of our project. So we intend to create the foundational framework. We intend to provide data sets, task definitions, and baselines for that, maybe also quite advanced and intelligent baselines. And we hope that other people in the community would take this up and scale all this, involving also various kinds of engineering challenges.
Yes. Gürkan said something. Yeah, thank you. I also feel like this will be very beneficial for the law domain or the medical domain.
Yeah, indeed. As you know, Max Eichler, so he is also part of this InterText initiative, and his work is in the medical domain, because in the medical domain you have many interconnected documents. And also we have discussed with people working in the legal domain, so you're completely right. They have many cross-references in their documents. So there, I think the first step is to build a good data set, so which we are not currently doing, but I think there is some corpus infrastructure to address that. If somebody had resources and interest, I think many interesting things could be done there, and they would also make a lot of sense, because in the legal domain, people really spend a lot of time on reading documents, extracting arguments, relating them to each other. So I think this technology could bring a lot of innovation in the legal domain. You're completely right. I mean, this situation with the interconnected documents happens quite in many knowledge-intensive domains, as I mentioned, but in every domain, I think there's this huge issue how to build a data set. I have talked a bit about all the challenges involved. So there's not just one text or one type of text. We have many different types of text. We have many authors. And I think this is a big obstacle, which we plan to address step by step in the next years.
Okay, so you have 5 more years, a lot of time. I guess you will have time to address.
Yeah, we have not even started actually. You know, the official project start is the 1st of April, but we also have some complementary projects so we can bundle more resources because it's really a big task.
Yeah. All right. Maybe I can get one more last question, if any. Okay, if not, then let me thank the speaker again, and Ilya too. Iryna and Ilya, thanks a lot for joining. My great pleasure to host you, and great to know about this exciting project.
Yeah,
Hope
thanks a lot.
in a shared task or in a workshop.
Yeah, so we hope that some of you will get interested in this and hope to grow the community around this research agenda. So thanks a lot. Great audience, great questions. We enjoyed this discussion.
Thanks for having us.
Have a nice day. Bye.
Bye-bye.
Bye-bye.